Welcome to the Explainer. Today, we're diving into a new machine from Google called Willow. Now, this isn't just any computer. It's a new kind of quantum computer, and it's designed to solve problems that, honestly, up until now, we thought were completely impossible.
But yeah, before we get into Willow itself, let's just start with a really big idea. See, there are certain problems out there in science that are so massive, so incredibly complex, that even our world's fastest supercomputers, well, they just hit a wall. They can't do it. The scale is just too much for them.
To get a feel for what I'm talking about, think about this. Imagine finding a name in an old-school phone book. That's a pretty simple search, right? Now compare that to trying to perfectly simulate every single interaction happening inside just one complex molecule. That second problem, that's the kind of impossible wall we're talking about.
And look, these aren't just some abstract puzzles for scientists to think about. We're talking about critical fields, things like medicine, climate science, where we are literally hitting the absolute limits of what our current computers, what we call classical computers, can actually do. They're just not built for the complexity of the real world.
But what if we've just been using the wrong tool for the job this whole time? Because a new kind of computer has just stepped onto the scene. One that's built from the ground up to take on the very challenges that leave our best supercomputers completely stumped. Right, so down at its Santa Barbara facility, Google's quantum AI lab has launched Willow. This is a machine specifically designed to do what regular, or classical computers, just fundamentally cannot.
At the very heart of this thing is a quantum chip with 105 qubits. Now you can think of these as the building blocks of quantum information. But here's the crazy part. Unlike the simple on or off bits in your phone or laptop, qubits can be both on and off and literally everything in between, all at the same time. This unlocks a mind-boggling amount of processing power that just scales exponentially.
And this really gets to the heart of the whole project. As Google's chief scientist Hartmut Nevin puts it, this isn't just about building a faster computer. No, this is about solving problems that were, until now, completely unsolvable by any other means.
So what does a machine that redefines the very limits of computation actually look like? Well, I can guarantee you it's probably not what you're imagining.
Yeah, this is not a computer in any way you'd recognize. There's no keyboard, there's no screen. It's a highly specialized scientific instrument, and it's all encased in this incredibly complex chandelier-like framework. And the whole job of that structure? It's to keep that little quantum chip operating at temperatures colder than deep space, right down near absolute zero.
But here's the catch. All that incredible quantum power comes with a huge vulnerability. See, building a machine like this means you have to overcome the single biggest challenge that has held back quantum computing for decades: errors.
You know that amazing ability for a qubit to be in many states at once? Well, that's also its greatest weakness. These quantum states are unbelievably fragile. I mean, the slightest vibration, the tiniest change in temperature, can introduce what's called noise. And that can cause the entire calculation to just collapse. It's like trying to build a skyscraper out of soap bubbles.
And this right here is where Willow is a genuine breakthrough. For years, the goal hasn't just been to build more qubits, but to build better qubits. Qubits that can actually fix themselves. And Willow has done it. It has achieved repeatable error correction. That means it can find and correct these tiny errors in real time. This isn't just some small improvement. It's the key that unlocks the door to actually useful quantum computing. It's a real game changer.
So, this huge breakthrough, it isn't just a theoretical win for a bunch of scientists in a lab. No, it opens the door to using this power to solve some of humanity's biggest, most urgent problems. And here's why this should matter to you. To all of us, really. Imagine being able to perfectly simulate new molecules to design life-saving drugs. Or what about creating hyper-efficient energy grids to fight climate change? This kind of power could also lead to massive agricultural advancements and give us far more accurate climate models. And you know what? It's not just potential anymore. It's actually happening. Willow has already tackled major benchmark problems. For example, it successfully ran an algorithm that simulates molecular action, the same kind of computation that's directly related to the physics behind medical tech like MRIs. So, while Willow and its error correction are a massive step forward, we're still just at the beginning of this journey. This milestone isn't the destination. Think of it as the solid foundation for an even bigger ambition. And experts in the field, they totally agree. This is a critical moment. For years, quantum computers have been, largely experimental toys. This represents a significant leap, moving the tech towards something that is way more practical and powerful. Because the ultimate goal,
The moonshot for the entire field is to scale these systems up from 100 qubits to about 1,000,000 stable, error-corrected qubits. And at that scale, we could unlock the full, world-changing potential of this technology.
And that kind of leaves us with one final thought. As we stand right here on the cusp of having a machine that can genuinely solve the unsolvable, maybe the biggest and most important question we have to ask is, what problems should we ask it to solve first?